All right, so hello and welcome everyone joining us today for the session from across the globe. Uh, Myself, Aniket, and I'll be the host for this entire session. Let's just wait for a few seconds before everyone joins, and then we'll start with the session. Okay, so I think we are good to begin. Let us first discuss what today's session is going to be about. So, today's session is going to be about one of the favorite materials in the advanced materials industry, and that is CMCs or ceramic matrix composites. In today's session, we'll be discussing why the adoption has taken place so slowly over the period of time. What are the manufacturing challenges that engineers face while working with CMCs? And we'll go a bit into the market dynamics as well. How big is the opportunity? Where's the biggest potential? And things like that. And to make this session better and more credible with us, we have two experts with us. Allow me to introduce them one by one. I'll start with Dr. Nagendra Nag. So I don't exactly know how to go about introducing someone with such a rich industry experience, but I'll try my best. So Dr. Nagendra Nag has several decades of experience in the ceramics and advanced materials industry. And throughout his professional journey, he has worked with some of the biggest names in that domain. Currently associated with McDanel Advanced Materials as the Director of Engineering and Technology. And he also happens to have a master's degree from one of the most prestigious institutions in India. So it's a pleasure for us to have you on board, Dr. Nag. I welcome you to the session.
Thank you. Thank you very much.
Yeah. So along with Dr. Nag, we also have Neha Singh with us, who is a senior research analyst at Stratview. And throughout her career, she has worked on several critical projects, consulting projects, and helped in shaping impacting decisions for stakeholders. She has worked closely with the ceramics domain as well, and she'll be guiding us with the market numbers and market dynamics today.
Thank you.
So, yeah, welcome, Neha. Welcome to the session. So I think we are good to start with the discussion, and let's talk a bit about CMCs first. So CMCs, as we know, they have been the magical material for quite some time now. They were introduced initially in the 1980s or 1990s, around that time. And since then, several claims have been made regarding the potential that this material holds. Several scientists, several experts have classified it as the material of the future, as we say it. But we all know that future hasn't come yet, and the adoption rate has been a bit slow as compared to the potential it holds. But as we are also tracking this space closely. We have observed consistently increasing demand over the past 5 years. And if we get down to the numbers, I can say over the past 5 years, we have seen close to 40 to 45% increase in global demand for CMCs. So, building on that, I would like to take my first question to Dr. Nag and ask him what he thinks has changed over the last 5 years from a technical perspective that has enhanced the demand and encouraged more professionals and more industries to move towards CMCs.
Thank you, Aniket. So it was a good start for the discussion. You mentioned the word magic. And like every magic that happens, only the magician knows how it happens. The rest of us are
Yeah.
supposed to not know how it happens. And that sort of is the story of CMCs in general. CMCs, like you mentioned, been in the 80s, it has been a hot topic, continues to be a hot topic, and I'm sure it will be a hot topic for another decade or a generation from us. The reason is the complexities of working with a material which is not traditional in sense of being like a metal or anything like that. So it calls for lot more attention to details, lot more attention to the magic that makes it work, and so on. So it becomes a field which is sort of understood by experts, but not always translated into being more production friendly because of the complexities I keep referring to involved. So what's changing? Well, I think few things which are going to make it interesting, and hopefully that is a new dawn for CMCs. We talk about additive manufacturing. That certainly has got a role that it can play in making things happen because of the flexibility or the knob, I would say, to make things that have not been done before. It gives you a additional flexibility in designing, in understanding how these materials need to be brought together, and so on and so on. So those kind of things are showing that there can be a path forward in making CMCs to be more generally accepted. Yes, there's still a long haul from the promise to actually making it happen that we have seen in CMC is the most challenging thing to do. But it seems it is very likely to lead us to a path forward to make the CMCs more affordable, more accessible to every day usage in the sense that it generally opens up the door for more people to play around with and bring in fresh ideas and so on. So that is the hope of the CMCs. And my wish is that it does not remain a hope forever. It goes into applications. And like we talk about, CMCs is always associated with the defense and aerospace and so on. But you also are seeing much more uh, embracement of the CMCs in different environment. And this could be something completely non-conventional, but the benefits are the same. And that's what people chase, the extra benefit it adds. And the hope is that that gets translated into a more tractionable path to help the CMCs come into mainstream products.
Okay, and that's great to know, Dr. Nag. So basically, additive manufacturing is one of the things that's playing a key role in driving the adoption.
It will certainly play a big role,
Yes.
assuming that the challenges of the materials, and you bring in also the component of AI designing, which is making things people would not have worked on happen because you have much more sophisticated tools to do the homework before you start working with it. So that gives you a additional leverage for making CMCs more process friendly because you can help in choosing the materials that could potentially be the reason for change in some of the process that are being adapted.
Okay, that's great to know. So, building on the same, I would like to now go to Neha and ask her how she thinks the industry is going to shape, given the current scenario, where the demand is going to come from, and how much demand can we expect over the next 5 years. Any comments on that?
Sure, Aniket, thank you so much. May I have my slides shown? Yes. Can we go to slide number 2? Yeah. So, when it comes to demand of anything, we have seen in CMCs that from post recovery of COVID to the structural broadening, now the market stands and behold at $3 billion at in 2025, and is on the way to almost grow to 4.5 billion by 2034. So the where the momentum is today. It is in the engine's hot section where the silicon carbide composites are actually compounding. So let me give you the honest trajectory where how because it was never a smooth ride for CMC since COVID. So the market stood at 2.5 billion in 2019, crashed to 1.9 billion in 2020, and then took several 2 to 3 years to come back the same line and standard as it was in 2019. It happened because of COVID. It also happened because of what we call was narrow body crisis that hit, and then now it is climbing back steadily, where we see a nominal growth when it comes to value, but we are seeing around 3.9% of the growth when it comes to the volume of it. When the volume runs more than that of value, the adoption actually spreads beyond the aerospace program. As already mentioned by Dr. Nagin, that aerospace is not only the thing that we are looking at, we are definitely looking at more than that. So we are looking for brakes, we are looking for industrial furnaces, we are looking for semiconductor tooling, and many more such applications that are being coming to. So now, when we think from now on, if we think from 2026 to 2034 window, the cumulative sales is nearly around 35 billion, which is actually twice that has been earned in the last 7 years. And the growth rate is not very spectacular, but it is very great in terms of market growth, that is 4.1%. So the momentum, when we talk about where the momentum lies, so you can see that the momentum doesn't is actually, when we talk about the value wise, the momentum is definitely with aerospace and defense. It holds around 70% of the value, and of that 80% is carbon brake, still making the CMC revenue. uh, but where it is actually shifting is the growth rate is lower in terms of A&D, and when it is compared with other same kind of applications into it. And similarly, carbon is the highest holder of value, but with the lowest growth rate, and hence SiC is gaining momentum with a 6% of growth rate into it. And where we can see where it is being used, so you can directly see that it is being used across GE's component ladders. So it is used in LEAP engines with 18 shout parts. It is used in 8,800 engines that is expected to be doubled by 2030. And then with the GE 9X entering into service on 777X carrier with 107 CMCs part across 5 hot section component. These all are actually escalating the growth of the SiC fibers in the industry. And just not to overlook that, we have seen a great momentum in electrical and electronics with 6.7% growth rate due to semiconductor processing, and nearly 6% of the growth rate when it comes to transportation. And that is what is actually generating good
Hmm.
hands in our industry.
Okay. That's great to know, Neha. Thank you for sharing the insights. It's basically all aerospace when we talk about CMCs. But like Dr. Nag mentioned earlier, that we also want to see this industry go beyond aerospace. So, building upon the same, I would like to ask Dr. Nag, which industries do you think can be the next growth generating epicenter for CMCs? Because aerospace have been in the picture for long, and they'll continue to be in the picture. But it's not fair to have a material with this much potential to be limited to a single industry, right?
True.
So
So, like Neha mentioned, the CMCs, when you refer to CMCs, the whole conversation is sort of more or less attributed to the carbon fibers. But CMC, in a broader outlook, is ceramic composites, matrix composites. And the ceramics are used for a reason because the metal just cannot do what they want. So where is it going to get more and more usage? So if you look at the growth in the electronics and the semiconductors that you're referring to, may not be using carbon fiber composites or anything. It may not be the driving force for that. But then you have many other exotics, well, not really exotic, but exotic in the sense of how you process them or how you make reality or how you make components out of it has to come from composites which give you very very specific advantage. And I can talk about, say for example, in the semiconductors or where plasma is out there, you have certain materials only that can work. But the problem comes in is that how do you make those materials in the shape, in the manufacturing, in the final finishing and all that. And making it as a composite gives you that extra additional flexibility because now you can bring two things together and make something maybe not the very best as the monolith, but you would still have the advantage of everything. So talking about CMCs, talking about coatings that go with the CMCs. All of these things are the ones that could lead the future deployment of these materials into practice and grow it. So I am quite optimistic in many of the things that are we are seeing in the industry. People talk about it from the R&D part of it. There's active work. So these things should at some point converge together and lead to solving some of the critical challenges in industries where they serve, and that would lead to more adoptions. So aerospace is definitely there, defense is definitely there, but we are talking about ceramic composites in a broader outlook. There could be other driving materials and other driving compositions, composites, macro composites, micro composites. All of this could help in moving the industry forward for adoption.
okay, that's great to know. So, like you mentioned, that there are several benefits that CMCs offer apart from just the high temperature tolerance. So, building upon the same, I would now like to know your opinion on what do you think about the barriers that are stopping from the adoption of CMCs, like that are stopping the other industries from adopting CMCs. Obviously, cost is a barrier because CMC solutions can be up to 5 times costlier if we talk about their counterparts. But what other than cost do you think can be the technical barrier behind CMC adoption?
The CMCs, as you mentioned, the advantage is the high temperature and so on. But when it talk about the high temperature, obviously the process also involves very high temperatures there. So that gives you much more limitations on how this can be processed into anything. And then you add on to the point where with the high temperature part comes the refractoriness and also the brittleness, two things which sort of makes this material sort of being skeptical about its use in real time practice. The reason being is that you will have difficulty in shaping it, you'll have difficulty in ensuring that they survive the lifetime that you would want. So, those kind of questions are debated upon even now, even not just at the industry level or the bigger meetings or even at the university level, because what are the real parameters that you would use to predict its lifetime and prediction about how it's going to behave It could be behaving a good in 1 year, but does it mean that you're going to get the same performance 5 years now? So those are questions which are very, very difficult to answer from an industry point also, and from the end user, because now you're expecting a material which is 5 times the cost, and you're going to invest in putting that into your systems, but are you guaranteed that you're going to get the best out of it, best performance out of it? That becomes very difficult to predict, and without those predictions, people remain skeptical about its end use, and that sort of limits it. Is there a way out? There could be a way out, best just by making sure that the material is robust and robust in every sense. But what is that every sense? A lot of testing, a lot of hard data about how it works in different environments. So those kind of things are time consuming and expensive to generate, and that also limits how these are going to be used.
So basically, it's not very easy to predict the performance, and performance uniformity is one of the biggest issues.
That's true. That's exactly where things fall off from the CMCs. How do you predict its behavior, and what kind of models you have? How sophisticated that model is? Is it really based on hard data or lab generated data? Because they may not match or converge at any point. So just the point of getting field data for a long time means that it has to be inserted in a realistic place and then get the data, which could be years together. So there's a lot of hard work and a lot of steps to climb.
So do you think like cross material compatibility is also an issue when working with CMCs? Because
Yes, but I would say that is the lesser devil of the whole thing, because you have tools that can predict mismatches and things, and you would be having the ability to match all of those things and develop newer materials, newer innovations, and so on. But at the end of this whole thing, does it really give its expected performance? And that has to come by extensive testing. And what are those techniques really are? I mean, are they going to test the material to its advantage, to its limitations, or is it just going to fall short of it? When does it fall short of it? Is questions really come back to limit these applications, and at the same time there's a lot of investment involved in setting this up.
so this must be the issues with aerospace industry as well. Like,
Absolutely, because any component you have to make for any of these applications means that you have to go through extensive certification, extensive documentation about all of those things. Those by itself is years long work. It's not an easy task, it takes a lot of time. And the people who can really invest those kind of time into making this into a mature thing have to be the big time players. And that means that they have the power of sustaining this work for a long period. And they do it because they know that this is the future for them. But for a smaller company which could have a great technology, but getting a material into the insertion is pretty much, it's a very, very difficult haul for them. So it sort of limits some of the innovations that could be there that could help us out. But those are practical difficulties that are facing the industry in general.
so basically, CMC right now is for the elite class only of the industry, elite
That's
players.
Unfortunately, it seems like it is. But like I said, that there are ways which other industries could adopt some of the benefits of the CMCs, and you don't need the best performing CMCs to help you out, but you would need the adoption of those to build other technologies that depend on it. And that's something that I can say I've actively worked on it, because it's not for aerospace or defense, but for other applications. The question is, how long does it take even there to mature? Because people look for quick returns. And the quick returns is not something that these materials will offer.
Okay. So what other major manufacturing challenges do people occur with CMCs? Yield loss and material wastage are some of the few ones that keep coming off
Right. So
often.
I think that the yield is something that is often debated forever because it's not an easy solution or easy question to answer. Yield for me could mean different for a yield for someone else, and so there's never a converging opinion about what is the yield. McDanel, where I work now, is a traditional ceramics, high-tech ceramics company. So we make thousands of parts every day, and they are not the same parts. So there are multiple different parts. And for us, the yield is something that is read upon differently from what could be for a CMC. So for us, it is what you promise to the customer as a date that you're going to give, and are we going to be meeting that with what we planned out to. So you have a process that you use to make certain things, and you already have built with years and years of it as what you have to make to get you 1,000 parts. But it involves different processes and so on. So you're assuming everything is in control and you calculate your yields and so on. But that does not always happen. And even for a company which has been there for hundreds of years, it's still a challenge because you would not have the yield from what you planned a month ago to what it's going to be the next month. So why and why? It's always something that is to be looked upon very carefully. And now you take that approach and you move it into a material of CMCs, which involves a lot more sophisticated processes, a lot more expensive processes, and so on. So at the end of it, if you stand out to say that I need to make 1,000 parts, what exactly is the amount of material that you went into making those 1,000 parts could be completely different. And can they sustain it? They have to transfer the cost to the part because that's the only way anyone can sustain. So now you have either a very expensive part, which is based on the yield that you do, and is the people are willing to spend that much for it, and if you have the leeway to make your own profit out of it. So it sort of makes it a very complex issue to deal with. Now, where are these yield efficiencies coming in? It could be due to the process that you're using, any of those things, but the bottleneck is what gets sent out. Is it to the design or the shape that you made? And that's where the bottleneck comes in, because if there is any machining or any finishing operation involved, it is the most difficult challenge to overcome, even for a monolith ceramic or for the more sophisticated CMCs, because there are not enough expertise, not enough machines which can guarantee you that this is going to meet exactly the dimensions, that the surface finish, everything that you need. So now you have invested in making those materials over a much lengthy process, and at the end of it, you cannot sell it because it does not match. And this is the practical experience of trying to sell something which is very difficult to sell. And now you are ending up with losses because you could not make what you set out to make. So that is the overall yield. So if you try to make one and then you ended up making 10 to give you one, there is no process. You got to have a minimum yield of something to make a process. So that's where things are not very, what I should say, clearly laid out. But a part, one part you sell could probably cover up everything that you invested in it. It's possible. And those are the materials that you would want to be in always, but it is the most challenging field to be in.
So till the end, it's very much a gamble, I would say.
It is because just because of the processes involved in the CMCs, you don't have much leeway to experience a failure at the very end. And if it does fail, it is lots of money that has gone into making it, which is now not, there's no return on it. And now that means that you cannot really sell it. We have had many occasions where you make a large part and then you make it and it does not give you the things that you desire, and you can chop it up and sell it so you have a yield or whatever it is, but that's fudging the numbers because you did not make what you set out to make, and that is a different story.
So that seems like quite a challenge. And uh, just wanted to ask this out of curiosity, because having a conversation in 2026 and not asking this feels illegal. Is AI helping in the process optimization for the CMCs in any manner in covering up for the
So
complexity?
yes. So the AI is being touted as a possible route to make many things happen. So yes, there is a potential, but the potential is more or less customized to every people. So now what work for someone is not something that you can just take and make it work for the other person. So you have to invest a lot in making it customized for you and so on, because every processes is different. And like we talked about, the processes for CMCs are a lot more stringent with very little scope for error. So now AI should technically fit very well into that kind of a scenario, because that's what it's supposed to do. Make sure that your very narrow path is sort of well understood and you follow the things. But is it been adopted everywhere? It's, people are still looking at it. There's no clear answer about how effective it is for anyone and where exactly it is effective, because the, like for example, even in McDanel, which has got maybe furnaces which could be 100 years old but working very very well, but what does it really mean? Can you use AI to predict how that furnace is going to really behave? Probably I would not say that is worth my money to invest in. So where exactly it would be? It would be in something that you would be setting up as a new project line or a new product line and so on, where you could start with the having the AI with you and help you out right at the beginning, and that's where I see the benefit. So for things like 3D printing or any of those things which are catching up pretty fast, there's so many things happening out there. So whether the AI would help you directly into that is, I would say, more likely than working with some equipment which are 50 years old. And you would believe it that most of the ceramic industries, they do work with equipment which are very very used for years and years and years. And I'm not going to take out a burner from a furnace and then put it, attach it to AI. It's not going to happen. So those were some of the practical difficulties in adopting AI. But newer technologies, newer processes, I'm hoping that the adoption of AI is built into it, and I'm sure it will happen at some point. But I don't know whether it's going to be in the next 5 years or 10 years. Hopefully, for the next 5 years.
So you are hoping that if AI has to enter, it has to enter right from stage one, right from the designing process.
Yes,
Mhm.
that would be the best shot for it to give you the best benefit of it. Using AI to directly work with existing processes which have matured over years is risky, and no one is willing to take that risk. They'll say, yes, it is curiosity, nice slides, nice everything out there. But am I going to be risking everything for using it? Probably not.
Mhm. Definitely. So, do you think at some point AI can also help in reducing the material waste by proper design optimization at a prior stage?
Definitely, I do see the benefits of it, and like some of the things that we talked about, CMCs and so on. So, as you can see, with the investment that goes into making a part, and you end up with a bad part at the very, very end, it is very difficult to recover from that. And those are where AI and other additional things could help out, in the sense that you feed in what kind of defects or anything you are seeing at the very end, and how that could link up with some of the existing processes that began doing it, or the raw material that went into it. That could be great beneficial, because now you start feeding in directly to the AI and seeing how any of the raw materials or any of the process that you are doing is going to contribute to the end effect. And that calls for sophisticated models and so on, but it is worth pursuing there, because the benefits are too much to say that it's not going to help.
So it's definitely a strong use case, but it's not there, right?
Not yet, not widely adopted. Maybe
Hmm.
there are people who are looking at it more closely, but those remain closed for everyone else, because no one wants to give out the story before they make the best out of it.
They don't want to reveal their advantage, basically.
No one wants to give out the competitive advantage that they come out with. That will be the same no matter what, just because of the investment that goes into making everything.
Mhm.
There's a lot more at stakes.
Okay. So, like another thing that comes up quite often when we talk about CMCs is its reusability. Like you mentioned, like I also mentioned earlier, it's a costly material, and if the part involves machining, then close to 15 to 30% of the material gets into wastage. So, what's your opinion on that? Are there any players who are working actively on the reusability part, and how that will benefit?
So that's an extremely difficult question to answer right now, because I don't think that technologies are mature to say that they can actually reuse it. Efforts are being done. There's no doubt about it. Efforts are being done everywhere. The green sustainability programs are growing with in every company that I am aware of. The green sustainability would mean how best can you recycle what you did and bring it back as a raw material for yourself. Most of the time yourself, because you are the one who can take the risk, not someone else. But it's a very, very big challenge, especially when you take a raw material which has gone through many, many iterations of processing, temperatures, reactions, everything else, and then you try to use it back as a raw material. Difficult, but people do have usage for using some of this into, say, raw material for a different application. Like if you take, for example, graphite, which is there for a long time, and you have it's carbon fiber made out there. So you can think of taking those things and building technologies where you could end up with chopped fibers and so on, which people try. How much they have succeeded is again not something that is very clear in the literature, open literature, or so on. But people are giving it a shot, because the resources are limited, definitely, and they're not going to get more and more. So, what is your uh, preference, or what kind of technologies you could use to make those existing materials to be recycled? So you need to have something that is sustaining it, because if you do recycle it, how much of it can be put back into the process, how much you have to build it into a different process, things like that, are not very, very clear. And I'm not sure when that would become a much more acceptable thing, but it's a very, very difficult challenge to overcome.
So by the end of the process, the material properties have changed so much that it's very difficult to treat it as a raw
Yes,
material for anything.
yes, that's
Mhm.
exactly the problems.
Mhm.
Because like,
That's
to
great to
make the
know.
material, your raw materials are very, very specific and so on, and now you're trying to incorporate a raw material which is vastly different from what you originally used. how do you bring that back into a process makes it very, very challenging scene.
But definitely worth the effort, right? Because the cost savings
Then
will be
people are
huge.
investing their time in you because green sustainability is something that is driving all these things forward, which is good. But the commitment has to be there to make sure that this gets moving quickly or progressively into making it a more realistic process.
Okay, that's great to know, Dr. Nag. Just taking a break from the usual discussion, and I think we should go to the comment section for a while as well. We have some comments from our attendees who would like to ask you some questions. Shall we proceed to that?
Definitely, yes.
Okay. Can you please bring up the comments? Okay. So we have a comment from Pranav, and Pranav asks, "How do you see China's investments influencing the global CMC competitive landscape over the next decade?"
So as everyone is well aware, China has got a very active program into moving forward with the CMCs, and they do have a lot of competitive advantage, especially with using the materials, very specifically the yttria, which is a very highly desirable material, the carbon industry, which is mostly graphite or so, which is almost 80% China out there. So now, when you have all of this in one place, then definitely there what happens in China influences almost everything that we can think of. So, for example, if we are using yttria, which obviously we use in many components of CMCs, whether it's coatings or it is meant for plasma resistance or any of those things, it is now something that we have to ensure is available and at the right quality and so on. And that's where our own efforts in being competitive with something that can come out of China is going to be affected very much. And it has started happening, and it's going to be there till the geopolitical scene is going to be clearer or so. And there's no guarantee when that geopolitical scene is going to be clear. But the investments are rapidly increasing, definitely. You see that with the work that they're putting out, the things that you see as products being listed out. So we can see more and more of those things coming into play, and now you will have the opportunity or ending up in a scene where you have to debate about the performance of some of these materials against the more conventionally made parts here. Because do we really, from the end customer of it, if he says that I can use these materials and I get 5 cycles of my time to do it, as opposed to buying the best material that anyone else can offer and get 10 cycles this thing or that. So the cost and all those advantages are playing out. How how it's going to come about is still not clear, because right now the the effort on the rare earth materials and all of it is impacting, and no one really knows for how long.
Yes, definitely. So the supply chain is definitely constrained, we feel,
Yes.
for this particular domain. So, Neha, you would like to add something on that regarding the supply chain or the issues that we can have for CMCs?
Sure, sure, Aniket. Uh, can I have my slide? It would be better to show
Yeah.
the things. So when we talk about what we call is the supply chain, right? So are we seeing the constraint today significant today? Absolutely. But it is actually structurally improving, and we will see a definite feel different change before 2030. So let me put it into something that is known as a small number of a qualified producers are there, which is actually what we say is only 3 third generation SiC fiber class are surviving today's hot section temperature that actually exists commercially. uh, a few to name: HI Nicolin type S fiber from the Nippon Carbon. Then we have Trinomer series from Ube, and then we have Ceramic from COI Ceramics. The aerospace flow is the first run through, which was founded by NGS Advanced Fiber way back in 2012, with the joint venture of Nippon, GE, and Safran with a share of 50, 25, 25 each. But GE has taken it to next step, and GE's Huntsville plant is the only large-scale Western source that is operating under this NGS license. So it is localizing the production, but is it an independent technology? No, it is not the independent technology. So what is happening is the demand curve is actually changing. If we see today, silicon carbide market, which was just half a billion in 2025, is now turning to be a $1 billion market by 2030 and the end of 24. So what is happening is the supply weightage in tons is actually carrying the demand line year on year. Where the where we missed most of the discussion is there any binding constraint in the count of the producers, or is there any qualification in the lock-in? Yes, the engine programs are one that are certified. So when we speak of that, then we have General Electric and Safran's hot section built on it. Switching, if we say that let them switch the producers. Switching means proving the part with the years of testing and in-service data that they have already gone through from past decade. Similarly, Ube has a capacity elsewhere doesn't lie in the GE program. So if we say let's shift it, it cannot happen. So in practice, three producer collapse into one such per program. Two of the three technologies actually lie with Japan. And that is why it adds a genuine geographic dependency when it comes to the dimensional change. So when we are saying it is structurally improving, then of course, as mentioned earlier, there are investments that are coming in and that will help in the structural change. Not now, but yes, in coming few years. For instance, GE has nearly invested $1 billion in manufacturing rounds in March 2025, with 22 million into Huntsville fiber materials and 20 million into Asheville plants. Then there is another consortium that is coming up from CY Ceramics, Honeywell, Pattern Whitney, and Rolls Royce with Oak Ridge, which they are actually targeting on the price factors of it. So today, if we say that the price is nearly tens of thousands of dollars per kilogram, the target is to achieve it at 1500 per kilogram. But we are not talking about the complex fiber that are being used. We are talking about new fibers that could be produced by nurturing it and can be used into different others uh, end users apart from that we are talking today from the aerospace.
Right. So what you're basically saying is that China does have the competitive advantage, but the existing market is safe for the players because going to a new supplier would require a lot of rework for the parts.
Definitely, it would. And if
True.
we talk about China's market, then China today stand as the second largest market, right, in the world when it comes to number tracking. And China in Beijing itself, it is well, like taking CMC as its strategic national technology with the help of C919 program, where they already have secured 1200 plus orders and commitment to create domestic engines and airframes. So this is the point where they are not simply sitting, but this doesn't exist 10 years before when actually we were talking about how hot strikes engines in CMCs. It is coming up today. So that is what new build-ups are adding. And that's how the shift is being taking place gradually, not instantly. Of course, it will take decades of time to have that shift.
So China will be an emerging market, but not anytime soon. That's what
No,
you're saying.
yeah,
Okay.
definitely.
Mm. That's Thank you for the opinion. Let's go back to the comments. Can we have another comment pulled up? Okay, so we have another comment from Priyanka, and Priyanka asked, which recent process innovations have had the greatest impact on reducing CMC production costs?
Uh, Difficult question to answer. What exactly is driving it, or going to be the single most innovation? The innovations are on many fronts, and I think my personally, what I believe is going to drive the CMC forward is coatings. And the reason being is that you have a lot more leverage, a lot more active work going on in building different coatings for the CMCs. And this could be the EBC coatings or many other coatings, which gives you the advantage. And that has got the chance of revisiting the CMCs because you can now push it a little bit more. And any small pusher you can get in terms of performance is a additional benefit for its usage. And there are those things happening out there. You still see some reports of someone 3D printing CMCs and all of it, but the very challenge of the robustness in the material, especially with porosities and all those things that come into a larger play, it's very difficult to say that you got some advantage of it. But a coating, on the other hand, is seeming to be lot more beneficial in making this work a little bit more towards your application. So I would say my bet would be the process innovations are coatings, whether it is using different techniques, laser ablation or slurry coating or plasmas or all of those things give it a extra additional edge to its performance. And that would what I would say is got the greatest impact right now because you already have pushed all your material to work for a certain process. What more can you get out of it? And it has to come from coatings.
That's very insightful to know, Dr. Nag. So basically, the materials are at their performance limit already, and so whatever little
There's always
innovations
a
is
scope for
possible.
improvement, but I don't see a huge innovation coming in for doing that. Yes, you have process refinements which are continuously happening, making tightening up your process to make it robust, all of those things. But where do you get that innovation which could leapfrog into higher performance has to be by getting the right coatings.
Hmm. Great, that's great to know. I hope that answers Priyanka's question. Then we have another comment from Deepak Kumar, and this is something which I think you also discussed during the initial section of the session. And Deepak asks, where does additive manufacturing fit in the CMC story?
So I think the additive manufacturing has more or less been looked at as a curiosity for CMCs. It's the additive manufacturing, for example, for alumina, which has been there for centuries and centuries, is itself challenging. And now you add a second phase to it, it makes it more challenging. Not that I'm saying that it cannot be done, it is done. But do you get a part which matches the conventional processing part of it? I'm not very convinced that you can because of the extensive characterization that would need to make certain thing work or not. And that's not happened with the additive because they're still making one or two parts which can be a lab curiosity or maybe even something that a company wants to say that I already there or there, but it's not something that has extensively moved on into saying that okay, I have a part, I can make 10 parts now and then try it out. It's not happened, especially with the CMCs, and it's just because there's so many challenges to overcome. So for someone to insert it into a very critical component, you need the extensive characterization and the data that would support its insertion. And that means that you need samples or things generated. And I don't think the additive manufacturing has matured to that point yet for CMCs. Some monolith ceramics, yes, you can say that they are reaching there, which has itself been a long story for them, a very hard story, but CMCs is still not there.
Mhm. So basically, additive manufacturing, which is known for its precision manufacturing techniques, is still not precise enough for CMCs.
Probably not.
Mhm.
Not that I would say it is to a point where you could go into a insertion of a component into a function. I'm not very confident that it has happened yet.
Mhm. Okay. So yeah, that's great to know. Then we have another question. I think how much time do have we? Can we take a few more questions, Dr. Nag, if you don't mind?
Sure.
Yeah. Okay. So we have a question from Mahi Sahu, and Mahi asks, "Are oxide CMCs a threat to SiC?"
I would not call it as a threat yet because they got space to coexist, which is good. But they both have their own role to play in anything. So oxide, yes, it is probably the more convenient way to manufacture something because much of your firing cycles and all is in a more controllable environment, which is air. But now, if you work with silicon carbide, you need a lot more infrastructure to make that happen. So that means that it's going to be added cost. So if I want to go for a lower cost material, which probably can survive for 4 cycles, like I mentioned, I may be choosing oxide, assuming that everything else is equal, just because of the cost. No matter what, the silicon carbide composites is going to be a lot more expensive. But at the same time, the technologies that would make oxide itself is not a very mature process, I would say. You can call it as being there, sounds very simplistic, but how many people really make that and sell it as something that you could just go buy instead of a monolith? So it's a very challenging environment, and silicon carbide has got a role to be at the peak at what it is because of the very specific advantages it gives. Oxides would be a step down, but they can coexist, and I'm sure they will coexist for a long time.
So basically, in any use case where performance can be compromised a little over cost, oxide will find their applications.
Could be used, yeah.
Mhm. Okay, great. So I hope that answers the question. We'll take one last question that is from Saurabh Sahu, and Saurabh asked, "How big a driver are hypersonics really for CMCs?" I think.
So the hypersonics is been emerging very fast, very quick, rapid growths are there. So that means that you got a lot more active groups looking at it in different ways. So hypersonics, just by the nature of it, demands a very challenging material to be there. So that means that the more active the groups are getting looking at hypersonics, and as you can see, the theater of hypersonics is evolving very rapidly. There's a lot more challenges, a lot more people getting into the game, and there is a reason because of the very advantage you get by hypersonics. But are the materials catching up to that? It is getting more and more active, and what people are trying to do, and we talked about coatings and things like that, is to see if you can use the existing materials to give you the very advantage to use in hypersonics by coatings or so on. And there is some success, but not something that has said that there is no other material or anything like that. So people are very actively looking at it. So is it going to be a big driver? I would think the CMCs are going to reinvent themselves for hypersonics, and that could become a reality there faster than many other places.
Okay, so the performance requirements of hypersonics are such that a lot of work still needs to be done on the materials.
It's become
As
a very active research
hmm,
field, and that are attracting more talent, more innovation, just because of the challenges are there. And like I said, your CMCs with some more innovations may have a chance to get faster tracked into those hypersonic fields.
so perhaps one of the fields which has the most work going on, like, regarding
Currently, I
CMCs.
would expect that that's just by going with the number of research papers, number of research groups being active in hypersonics, it's growing very fast.
Looking at the current global geopolitical situation, also, I would say it's going
Yes,
fast.
absolutely.
Okay. So, yeah, thank you for the insights, Dr. Nag. So, we have a few more comments, I think, but we are past the 1 hour limit. So, we can have those comments answered through email. We have the profiles from which the comments were asked. For now, to end this session, I would like to ask one closing question to both the panelists, starting with you, Dr. Nag. Where do you see the CMC industry headed in 5 years, and what innovation do you think needs to be done for the industry or for CMCs to become more mainstream?
Right. So I'm very, very positive about the growth of CMCs. I'm sure that because just for the reason that people are looking to stretch the performance of materials, and there is not much more you can do other than look at the CMCs and see how we can make it robust. So if you ask me what could be the biggest effect that could have on the CMCs, is the robustness of the CMCs by itself. So anything that could be technology that could help us in understanding the robustness, and that again comes by, it could be non-destructive evaluation or more and more of those techniques linked up with the AI, which could process this and tell us very early on what are the possibilities of things going wrong in the material or the process, would be a huge advantage, because that's where the effort lies. Because of the process, catching it at the very end is expensive and not going to give us anything good out of it. But if you use some of the NDE techniques and see what this defect characterization, what exactly they are, how do they look, and can you catch that early in the process, which whatever way you can, and that's where the AI could come into effect, where you are looking at seeing all those images coming out from NDE and linking it up with any particular process and seeing where it is happening would be a huge advantage. And I'm sure there are a lot of people who are trying to get to that. So I'm thinking that more and more work that is going on to it to catch that would definitely help in making this material drop its cost, or any of those things that could help in adopting it for more applications.
Mhm. So early detection of errors
Yeah.
needs to be something that needs a lot of work and that could provide a great advantage.
Yes.
Mhm. Okay, definitely. I also think that will help a lot in the cost reduction because uh, rather than knowing once the part is almost made, you can you will still have a few stages left for improvisation. So that will definitely help.
Right.
Now, yeah. So now coming to you, Neha, you would you like to add anything on that? And what's your opinion? Where do you see the industry in 5 years?
So if I may have a slide for that. Uh,
Yeah, sure.
so let me go straight to that part of it. So I personally think that fiber, like it's very unglamorous choice that we are having with the fiber today. So according to me, the fiber is acting as a tax on everything when it is going downstream. So it's a price on your prototype, it sets penalty on every scrapped component, and definitely it decides which industry can afford that material class and which cannot. So the batch process fiber, which is now five figure right now in the CMC and is only proposition for aerospace, but if it can come to that four figure, then it definitely opens door for transportation, energy, and industrial application, which can definitely coincide directly. And there are several programs going on all around the world in which, without hypersonics, without the CMCs, such examples such as hypersonics or the aerospace things cannot be formed. So now, when we talk about the multiplier, like, is this material a breakthrough alone? Does it leave money on the table? Definitely, AI earns that thing. And I think it has three layers in which I would like to explain how AI may help this particular industry as per the leading edge are. Like, AI has earned its place across three different layers. First is in design information simulation. As we talked earlier, it can be included in the very early stage of it. So, for example, the fiber is very expensive. It if into AI, the cost and trial and error prototype can be definitely be secured. Then in processing, you can have in situ sensing plus machining tools, which can have help in hold of multi CPI densification. Then definitely add the inspection and automation time, where you can definitely detect the flaws using AIs. But is it done today? No, it is not. It's actually more of a speculation, and they are trying to do it. But there are certain patents that have been found. In 2026, a patent was formed by Boeing's, which definitely describe robotics and CMC, guiding machine vision into the closed loop. Even GE Aerospace has filed through repair by design in situ diversification, so as a damaged component repair rather than just written off and fold off inspection technology in the investment round. Just a few weeks ago, here, the AFRL awarded AeroVironment with $20 million of ceramic contract pairing additive manufacturing with embedded sensor for the real-time health monitoring. These are very few examples where actually everyone is pushing to invest in looking for the vision for today to put the high cost fiber and yield into a very good kind of a product in the upstream value.
Okay, great. So this is pretty much almost in complete harmony with Dr. Nag already said regarding the early detection of the errors. But you also want cheaper fibers to be included.
Definitely.
Okay, yes. So that's great to know. Thank you for sharing that, Neha. So I think we are about done with the comments and today's discussion. Now I think it's time to bring the session to the end. So uh, since we have a few comments that are left unaddressed, but we'll attend to that later. So for the closing of this session, I would again like to thank Dr. Nag for joining us today and taking time out of his busy schedule. I hope it was an insightful session for you as well, and you enjoyed being a part of it.
Thank you, Alinke. I really enjoyed myself listening to the comments from Neha, the questions, and of course, you are moderating the talk. It's a very good experience.
It was the pleasure was all mine, Dr. Nag. It was great connecting with you, and we hope if opportunities allow, we'll connect again in the future for similar endeavors.
Definitely.
Yeah.
Thank you.
Okay. And thank you, Neha, for joining us today and sharing the insights with us. And thank you to the audience as well for being a part of this session and dropping their doubts and interacting. I hope you find some insightful takeaways. from today's session, and we keep conducting such sessions every month. So if you want to be notified earlier, you can just subscribe to our page on LinkedIn. So thank you, everyone. I'll take my leave and have a great day. Bye bye.
Thank you.
Thank you, Aniket.
Thank you,
Thank you,
everyone.
Dr. Nagendra.
Right. Thank you.
Thank you.